Hi, today I'm going to walk you through the MoreFuel lab provided by Kansas Corn Stem. I'm James Burk, lead teacher with Kansas Corn Stem. Today I'm going to walk you through the MoreFuel lab provided by Kansas Corn Stem. The purpose of this is to look at another value-added product, another biofuel that can be produced from corn or soybeans, any other plant material. The materials you're going to need are some methanol or ethanol, some potassium hydroxide, eye protection, definitely want that, a sous vide or a warm water bath speeds things up a little bit, and you'll also need some corn oil. So the learning objectives, students should be able to explain why biodiesel and other biofuels are important alternatives due to the source of the carbon involved. Explain how biodiesel is derived from three components. There's a triglyceride, in this case from the corn oil, an alcohol, could be either methanol or ethanol, and a catalyst, in this case we use potassium hydroxide. And identify and test different fuel properties like solubility, some viscosity, temperature changes, things like that, so comparing viscosity. So in this case you need to know what diesel is. Petroleum diesel is a hydrocarbon that is refined from crude oil. It's typically between 10 and 15 carbons in length. So this is the carbon molecule down there, the hydrocarbon molecule. And the average is about 12 carbons in length. So this is about 75% of petroleum diesel is saturated hydrocarbons. 25% are aromatic hydrocarbons, which can have some other properties that you might not want to handle too much. The difference with the carbon, old carbon has been trapped underneath the ground for millions of years. It used to be in algae and it was trapped. And when in petroleum, that is pumped out of the ground in an oil rig, refined, and in diesel, when we burn it, the carbon that used to be underground is now in the atmosphere. And that's what scientists are concerned about with rising carbon dioxide levels. Another problem that can show up in diesel, and they've worked on cleaning this up, is there's other things that come up. There's some sulfur and other compounds, and when those are burned, they can produce sulfur dioxide, and that's one of the major components of acid rain. That's something in coal, it's in a lot of the fossil fuels that are, and they do have ways to work on that. The big difference in biofuels, and this works in ethanol or biodiesel, any biofuel, is the source of the carbon. Instead of coming from underground, the plants that are grown are pulling the carbon dioxide from the atmosphere and making sugars or oils out of those. So that's where the carbon molecules or the carbon atoms for the diesel fuel are going to come from, or for the ethanol. So it was already in the atmosphere, so when that gets burned in a diesel engine, the carbon dioxide that goes back was already in the atmosphere to begin with, so it's just recycling it. Actually, a lot of that carbon gets fixed into the ground. Different farming techniques, they can get more carbon sequestered into the ground. So the chemistry of renewable biodiesel, fats and oils are triglycerides, and fats are typically from animals, oils are typically from plants. So there's a glycerol on this end, which is a 3-carbon alcohol, and fatty acids on the other end. So there's 3 of those, that's why it's a triglyceride. If you get blood work done, a lot of times they'll check triglyceride levels. Saturated fatty acids, if you ever hear of saturated fats, those are pretty straight chain, and then there's unsaturated fats that come, fatty acids that come from plants typically, and you can see they're much more bent. So the problem with saturated fats in a diet would be that at room temperature or at human body temperature, they stack up pretty well because of those straight carbon chains. So they tend to be solid at room temperature. So if you think of things that are solid at room temperature like butter or lard, things like that, those are saturated fats. Where oils, like the corn oil that we're going to pour out here in a second, has a lot of bent chains, so when they arrange, they don't stack up very well, so they stay liquid at room temperature. So turning triglyceride into biodiesel, we need to get these fatty acid molecules off of the glycerol, and that takes a catalyst, potassium hydroxide, in an alcohol. So that's the catalyst that we're going to add. Just removes the glycerol and makes fatty acid methyl esters. and that is technically what the biodiesel runs. If you use ethanol here, it will run a little bit, it'll take a little bit longer to produce, but it makes a fatty acid ethyl ester. Works pretty much the same. So a lot of ethanol plants will harvest the corn oil or buy the corn oil and produce biodiesel. There's another process, renewable diesel, which doesn't make a fatty acid methyl ester. It makes exactly the same as regular diesel, and it uses a catalyst reaction and hydrogen to strip the glycerol off, and it makes exactly what you would get in petroleum diesel, but they can control exactly what molecules are coming out and the properties involved. So to produce biodiesel, first of all, you have to be very careful. The methanol, you don't want to get that on your skin or inhale a lot of it, so I typically do this in store it in a fume hood overnight. And you want to make sure you have protective eyewear, things like that. So first thing we're going to do is produce our catalyst. So we're going to get between 0.2 and 0.3 grams of potassium hydroxide, and I had that weighed out here already. This is one of the pellets in the potassium hydroxide is about 0.1 grams. This was exactly 0.3 grams. So we'll go ahead and add that to our centrifuge tube. Get him all off there. And you don't want to prepare this very much before you run the lab. You don't want to get a new. You don't want this potassium methoxide sitting around very long. So you take 5 milliliters of methanol and add that to your potassium hydroxide. Careful not to get that on you. Put the lid on and you swirl it around. It takes probably about 10-15 minutes to get the potassium hydroxide completely dissolved. So once that's dissolved, you're going to need your triglyceride. In this case, we're using corn oil. That's what they would use it, get from the ethanol plants. Soybean oil is another major source of triglyceride. So we're going to pull about 25 milliliters of corn oil. So I take it up 2 milliliters above the zero there. That's 12 milliliters. Let's add that to our catalyst. Now I have 12, so we'll put 13 in this time, take it up 3 above the zero. That's 13 milliliters. That'll give us 25 milliliters of corn oil, or the triglycerides. Try to make sure we get all the oil out of there. Okay, now if you notice, the oil is at the bottom and the methanol or the catalyst is at the top. And so you put the lid on good and tight and gently invert that a few times. Try to get that mixed up good. Don't want to shake it up. And then if you want to speed the reaction up, you can use a warm water bath set to 50 degrees Celsius. And just set this in a test tube rack. You want to, again, vent the lid just a little bit so it doesn't build up any pressure with the increase in temperature. And typically let that sit overnight. Okay. When you come in the next day, you'll see that this is inverted. Instead of having the methanol, the clear methanol layer at the top, you'll have this darker layer at the bottom, about 5 milliliters again. And that's the glycerol that's been taken off. And then above that is the fatty acid methyl ester, or the biodiesel. And if you wanted to run that through an engine, you'd want to wash it several times. Again, for this lab, we don't, and the workshop, we have to turn this around pretty fast, so we don't go through the washing steps that you would need to do to actually use that in your diesel engine. So that's what it takes to prepare that. Now we're going to run some simple tests on it, see if the properties have changed much. If you're making a larger amount, typically what they'll do is just have a valve where they can drain the glycerol off of the bottom. But in a smaller amount, we're just going to pipette the layer. Try to get where you can see that there. Off the top into a different, we'll just leave the glycerol at the bottom. Turn that so you can see it a little better. So you stay above that layer. You don't have to get it all off, just want to try not to get. So then you have some glycerol with a little layer of biodiesel at the top there. So that's our biodiesel sample. One of the other samples you should have is some renewable diesel. At the Garnett plant here in Kansas, they make renewable diesel. Again, that's a catalyst-driven process. So this doesn't have the fatty acid methyl ester in it. This is just a hydrocarbon. And again, they can control exactly what molecules are coming out and control the properties on that. So in the wintertime, you can make it so it doesn't gel up. That's one of the challenges of dealing with biodiesel is in the wintertime when it gets cold, it tends to gel a little faster. And they measure the cloud point, or where it starts to cloud up a little bit and become translucent. And the lower the cloud point, the better it will handle cold temperatures. So that's our renewable diesel. And then we'll do one of the original triglyceride here, so we can compare our biodiesel with what we started with. It's kind of hard to get all the corn oil out of there. It really wants to stay in the thing. So I'll just put that one there so it doesn't leak. It's best to have 3 pipettes. For this one, this is our renewable diesel. And for a viscosity test, it's kind of interesting to watch, see how long it takes to flow out of a pipette. So we just use a gravity feed to drive it. This is our biodiesel. Put the lid on our renewable diesel here. So for this lab, for this part of it, the viscosity test. We're going to use a stopwatch, and I typically just use my phone, and I'm going to take it right up to the 11 mark there, and I'm just going to see how long it takes to drain down to the, well, do 10 milliliters, and you can do whatever, but it will take it down to here. So that from 11 to that, or from -1 to 9 is 10. So I'm just going to open the valve right here and let gravity pull the oil, or in this case the biodiesel, out. So about 4.43 seconds. You can run a couple trials of that, and there's a data table in the lab right up where you can record that and average that one out. Again, so we're going to repeat that with, I have this in the wrong one. This is the renewable diesel. Do the exact same thing, pull it up. One above the 0 is marked -1 right there. And sometimes it's hard to tell when the last drips get out, so it's easiest to go from -1 to the marked at 9 here. All right, so we'll do the same thing here. Going to reset it. So 4.43 was for the biodiesel. So 3.65 for the renewable diesel. And again, getting an average of that and having a group of students working together where one can run the stopwatch while the other is running the pipette works a little handier. And this is the corn oil. This is a little bit thicker, so we'd expect it to be slower. So we'll try this as well. And yeah, that took about 11.1, 11.2 seconds there. 11.16 is what it came up with. So you can see there's a big difference in viscosity. Now what's interesting is as the temperature changes, you'll get bigger differences in viscosity, which happens with oils. That's why motor oil weights have the 5W30 and 10W30 and things like that, is how temperature deals with this. So you can run this at different temperatures using an ice water bath or warm it up. You'll see more differences if you go down using ice water and cooling it off a bit, letting it settle to a different temperature, maybe 10 degrees instead of room temperature Celsius, and running that again, and then going colder. You can even use some salt in with some ice to get it really cold, but you'll start seeing bigger differences. So the renewable diesel, they can control the cloud point. The biodiesel, you're kind of stuck with whatever fatty acids are in the triglyceride. And then the diesel is, yeah, kind of the same thing. You get different blends as they're refining it. All right, another interesting test is solubility. One of the problems that biodiesel ran into early is it's very capable of dissolving plastics and other things, and some engine components were made out of that. So for this test, you'll need a hole punch, single hole punch, and a styrofoam cup, and just punch some circles. In this case, I just need 3 with a hole punch. And you should get 3 fairly identical styrofoam discs. And we have our 3 fuels, 2 fuels, biodiesel, renewable diesel, and corn oil here. And just to compare what happens to the styrofoam disc in each sample. So just drop it in, swirl around a little bit. And you can come back and check this at 3 or 5 minute intervals. So again, it's floating in all of them right now, meaning it's less dense, which we would expect with styrofoam. Okay, so it's been about 5 minutes, so we'll go ahead and check these. Our corn oil disc doesn't look much different. The renewable diesel, since it doesn't have that methyl ester on the end, that hasn't changed. And our biodiesel disc has completely dissolved. You might see after 5 minutes a few little flakes of it, but it's pretty much gone. So again, newer engine designs have helped with that, where they don't use plastics or rubber materials that are soluble in the biodiesel, but the renewable diesel doesn't have solubility issues at all with plastic components. So that concludes the lab. To see more, visit kansascornstem.com.